Hi, this is Professor Jen Mei Chen at California State University, Long Beach. In this video lesson today, we'll look at function behaviors and how we're going to use function behaviors to tell us where the local extrema values happen. We're oftentimes very interested in spotting trends from functions, such as increasing or decreasing behaviors. This information, in turn, allows us to spot where the extreme values happen. For example, assume that you have a function that is nice and continuous. Then you will have to reach a maximum if it starts to go up and then goes down. On the other hand, if you have a function that started to go down first and then climb back up, it will have to reach a local minimum. In this first case, we say that the function increase first and then decrease. And if we label our x-axis this way and call this point on the x-axis x equals a, then we would say that the function increases from negative infinity to a and then decreases from a to positive infinity, and it reaches a local maximum at the point x equals a with the function value f of a, if this curve is actually described by some sort of a function f. On the other hand, if we do similar things and draw an x-axis for this graph and say this function is g, then at this point where a function kind of changes behavior from decreasing to increasing, we label this as x equals b, then we would say that the function first decreases on an interval from negative infinity to b, and it increases from the interval from b to positive infinity, and it reaches a local minimum value at x equals b with the value of g of b. In a lot of scenarios, these functions actually depict real-life situations, and being able to describe these characteristics allows you to communicate very intelligently in writing. A lot of times you read newspapers and they actually have to talk about the trend, whether or not it's increasing or decreasing, whether or not it actually attains a maximum or a minimum point at some point in time. So be able to actually spot those behaviors allows you to actually write about them in words. Next, let's actually define these concepts more precisely using the definitions next. First, we define f to be increasing on an interval I if some condition happens. Alright, well, let's look at the picture to see what condition needs to satisfied. Well, a function that is increasing needs to look like this. If you label the first point where it kind of starts, x1, and a second point where it kind of ends, you want to compare it to, then if you look at the function behavior at x1 and x2, you would notice that the f of x1 will actually have a smaller function value than the f of x2. So the function needs to be increasing if every time that I take a point that happens later on the x value and compare its function value to the function value in the previous x value, it needs to be always bigger. Okay, so I can fill in a blank here. A function is increasing on the interval I if f of x2 is greater than f of x1 whenever x2 is greater than x1. You actually have to make sure that there is no equal sign in this, because if you allow for equality to happen, that means your function value can actually do this. If this is x1 and this was x2, you allow that f of x2 to be greater than or equal to f of x1, then you would allow this behavior where you just kind of stay on the same function value in that time interval. But then you can tell obviously this is not really increasing. This is just what we call the non-decreasing behavior. But we don't want to allow this behavior to happen. On the other hand, we say that the function f is decreasing on the interval I if the function value at the second point is less than the function value at the previous point whenever we have those two values compared. Pictorially, this means that if you label the first point x1 and label the second point here x2, then the function value at the second point needs to be less than the function value at the previous point. So then it has to be higher in the y direction for that first value. So the function could do like such behavior here, right, to actually be satisfied as a decreasing behavior. I really want to emphasize good writing in terms of describing the function behavior. You want to use all the keywords as function is decreasing on the interval. Okay, you don't want to just say it's decreasing. Writing a newsletter and you just say that the trend is increasing, and while the trend really looks like this and that, So people will be confused, what do you mean by increasing? Really, it's increasing on a certain interval first, and then it changes behavior to a decreasing behavior. You got to be precise where exactly on the interval your function is going up and where it's going down. Before we move on to the next set of definitions, I want you to practice using this language of increasing, decreasing behavior a little bit. Here I'm going to give you a function which looks like the following. I want you to determine the intervals on which the function is increasing, and as a separate question, determine the interval on which f is decreasing. Now pause the video and think about this. Write your answer in interval notation for this. So for intervals on which the function is increasing, you're going to start looking for function value that just keeps going bigger and bigger as we move from left to right on the real number line. So if you traverse the real number line from the left hand side here, as we go through the curve, we notice that the function value actually keeps going up as we travel along this curve here, until we hit this point on the curve where the function value actually started to go down at that point. So the first interval the function is actually increasing is going to be from point A to point B. Okay, and when is the next time the function started to go up again? Well, that's about when it starts at C and all the way up to the point D. And notice that we have an open circle on the D here, so I'm going to describe that interval as C to D with an open braces on the D. To connect those intervals, I'm going to use the union notation, because on the other hand, for intervals on which f is decreasing, you're going to start observing function value dropping as you go from left to right. So if we traverse this curve over here, you'll notice that it's getting a smaller and smaller function value, going from some positive number here all the way to 0, and then start to get negative function value all the way until the point C. So the first interval, it's decreasing. It's going to be from point B to point C. And we start looking for the next set of intervals that the function does that. And we notice that it's from the point D and all the way out to the positive infinity, because it's going to continue this behavior all the way to infinity, and that's what this arrow sign is indicating there. So it's going to be union the interval aside point D out to infinity. Next, we want to use the increasing and decreasing behavior to tell us where the local maximum value and minimum value of a function happens. We say that the function f attains its local minimum at x equals a with the value f of a if function value f of a is less than or equal to f of x for all the x near a. On the other hand, we said that the function f attains its local maximum at x equals a with value f of a if f of a is greater than or equal to f of x for all x near a. Let's use a picture to illustrate the definitions. Suppose the graph of some function is given here. For simplicity's sake, let's not worry about what actual values these functions go through, but instead just label some critical points here that are of interest. The red lines here are just visual aids to tell us where the x locations happened, where the function has its peaks and valleys. So let's go ahead and label these points on the x-axis. Let's call this A, B, and C, D, and E. And this is on the x-axis. The height is given by f of x. Okay, so let's look at the first point here. So let's start with the first point here, x equals a. Okay, if you were to travel on this curve, and imagine you're a little ant traveling on this curve, because you're an ant, you can only see very, very little ahead of you and also behind you. Okay, so then if you're going very, very slowly along the curve, and you keep going, and every time you look back on what you've traveled, you notice that the function value is actually smaller than your current point, right? All the way to this point right here. Okay, at this very point, you're kind of like on the top of the peak. Now, I can see it because I'm a human. I'm looking as more of a globally at this picture, so I can see what that's obviously a peak at that point. But for a little ant, it can't tell, right? It doesn't know if it's reached a peak yet. Now, if you, the ant, look backwards on the places you've traveled, you notice that the function value at the previous points are always going to be smaller than the function value you're currently at, right? For example, the function value at that point obviously would definitely be smaller than the function value than you're currently at. If you now look ahead a little bit on the function value over on this side of the curve, right, these guys, It also has function value smaller than the function value at your current peak point. With that in mind, we go back to the definition for local maximum. We see if this actually makes sense. For all the points near A, meaning backwards and forwards, if you look at the function value at those points, it will always be smaller than the function value at the peak point. All right, A being the peak. This statement definitely makes sense. So if that's the case, then we call x equals a local maximum for the function f with the local maximum value of f of a. On the other hand, if you keep going, if you this little ant keep going, and eventually you travel all the way to this point, and then for human we can see that's actually a value point, which is considered as a minimum point on that curve. And if you now look backwards on the function values you just traveled on, you notice that you're actually at a higher function value than the function value at this valley point. Okay, and then if you keep on going, start traveling, going up, and the function value that you get at those points ahead of B are also going to be higher than the function value at B. So this actually satisfies this other definition. For all of the x near A, meaning forwards and backwards, the function value at those points is always greater than or equal to the function value at the local valley. If that's the case, then we call that the point A a local minimum, and we say that the function attains its local minimum at this point x equals A with the local minimum value of f of A. So with this definition, you're basically just imagining you're a little ant and comparing function values around you. And if you're actually greater than everybody around you, you must be a local maximum. If you're smaller than everybody around you, then it must be a local minimum. For this definition, we would call the point x equals a local maximum. We would also call that C is a local maximum. We would also call E a local maximum. We would then say the point B is a local minimum and the point D also a local minimum. In complete sentence, I would say f attains a local minimum at x equals b and x equals d with the function value f of b and f of d, with respectively. I will also say that f attains a local maximum at x equals a, x equals c, and x equals e with the function value of f of a, f of c, and f of e, respectively. A side note for this definition is that we typically don't consider the endpoints as being a local minimum or a local maximum. So for example, from this graph here, these 2 points would be called the endpoints for the function f. So if we call this point say h and call this point here an r, then I would not consider x equals h a local minimum, and I would not consider x equals r a local minimum as well, because these two are the endpoints for the domain for this function.